Good morning, Nathan.
Morning.
I'll give few minutes for people to join. Okay. Do you want to test out anything?
Huh?
Do you want to test out your screen sharing or anything?
We can also leverage that to perform geospatial task in machine learning. In the previous time, one of the big data set that has the general image is the ImageNet, and they produce a lot of the pre-trained model, and it still has been the benchmark data set that people actually use to evaluate the performance of the computer vision models. So and there are so many tools that you can use for the ImageNet for the transfer learning. Segment anything is another model that has been used in the geospatial. I have put the link in the slide if you are interested in learning more about those. The CLIP model is another model that has been trained on a really large data set. Next is also saving time and resources. As we said, in order to train the new model from scratch is required label data and also computational resources. If you use the transfer learning, basically you have the head start from the previous knowledge that the model has been learned. And also, the transfer learning can also boost the model performance, because when the model learn from the vast, large data set or diverse data set, it can learn about a really general idea of the data or general idea of the structure of the data. So that can be applied to the new or specific knowledge of our task. So next we will talk about how transfer learning actually works. The core concept of the transfer learning is that is not about just reusing the model, but it's about reusing the knowledge learned from the one domain or the previous task that the model has been trained on, applied to the new task that related to that previous task that has been trained on. But why it actually works? Because in the deep learning model, the initial layers or the layer that's closer to the input data, it will learn about the general features such as the edge, the texture, or a really general idea of the object itself that are, and we hope that is useful across the different tasks. And then the higher layer or the layer that closer to the output is learn about the specific task or specific feature that it has to look for in order to perform the task. On the right-hand side, there are two examples here. The top one is, as you can see on the top, the input is the image of the elephant. The first layer closer to the elephant's features, it learns to detect where the edge or the curve of the boundary of the object are. And then it combines those edges and curves into some part. And then the closer to the output, that output, whether it's elephant or other kind of animals, it combines those features into the outline of the elephants. So as you can see, the closer to the output, the more specific with the task or the identification of the object that you need. On the bottom example here is the input is the image of a dog, and the two images on the right hand side are the shallow layer, the activation model, or the focusing point of the model on the image input itself. As you can see in the shallow layers, it looks everywhere. It looks at the edge of where's the edge of the dog, R's. But in the deeper layers, you can see that it's look at the ear and the eyes, basically on the head of the dog, to identify whether the image is a dog or some kind of animal or other objects. And that's basically the core concept. Is because why transfer learning work is because the model that learned from the large data set or a diverse data set, it's really good at identify their general features of objects. And we hope that those will facilitate the learning of the specific task in the transfer learning. So in this presentation, I will talk about the two main approaches in the transfer learning. If you actually learn about the transfer learning, there are many kinds that you can actually do the transfer learning. You can do the features transfer, you can do the weight transfer. But in this presentation, I will talk about the two approaches that it can be done quite easily, and you can test it whether it works or not quite quickly, so that you can try and you can see whether that could help with your task. So the first one is the feature extraction approach. Basically is to reuse the knowledge learned from the large data set. So basically you use the pre-trained model as a whole without any training or further training or change of the weights in the model itself. You use the pre-trained model as the feature extraction, and then you use the classifier from to learn from the input from the feature extraction model. So you freeze all the early layer. Freezing here is mean that no further adaptation or learning, changing of the model. So you use it as is. And then you use that model and train only the classifier layers for the new geospatial data. So the feature extraction is on the right here. As you can see, we have the pre-trained model, and then we create the new classifier, and then we only train the classifier here, and then all the model input to the last pooling, we freeze them. We don't train it further, no learning, anything. That's why this approach is actually will require less resources for the training, because when you train, it's only adapt only these last two layers or the classifiers. The next approach is the fine-tuning. So this fine-tuning is basically we adjust and refine the pre-trained model to the new task. So we unfreeze some layers or all the layers of the model, and then we adapt them or we adjust the weights or the knowledge inside the model to specific geospatial features or the input. And then we use one key thing in the fine-tuning is that we have to use the smaller learning rates to avoid overwriting the pre-trained knowledge in the model itself. So for the fine-tuning approach shown on the left here is that we start from the pre-trained model, same as the feature extraction, and then we use the whole model, and then we, as you can see, the new model is also the trainable, all the trainable parts. Sometimes we can change, we can freeze the shallow layers because we believe that it's learned just the general features of the objects. So we can freeze the shallow layer, and then we unfreeze the deeper layers in order to adapt to the new specific task. Those are the two approaches that we will talk about here. And next is we will go into the demo. For the demo, you can go to this website, go.illinois.edu/GOTL-iGuide. Or I can give you the link So we go to the iGuide platform. So this is the iGuide platform. I can send in the chat. And then if you go to the iGuide platform, you go to notebook. You see that I have the notebook here for this demo. And then if you click it, you can see, thank you, Anand. You can see that we have all the information here. For those who doesn't have the account for their platform yet, you can click, I can log out first. And then if you click run this notebook, oh, I can log out. If you click run this notebook, you will come to the welcome screen. And then you can use the CI log on to sign in to the Jupyter environment. You can use your institution account to actually log in. I will use the UIUC. And then when you log in, the system will automatically open that notebook and also clone all the information or the required data into your Jupyter environment.
So Nathan, we can maybe pause a minute to see if people are having any problem opening the notebook Nathan shared. So you should be able to, as Nathan showed you, click the link and open it on the iGuide platform. If you have any trouble, let us know. Either on chat or you can speak up.
Yeah.
Small enough group.
So does anyone successfully open the notebook? Give me a thumbs up. Thumbs up.
Yeah.
Thank you. Thank you. Thank you. Okay. So in general for this notebook, I try to make it as self-contained as possible. So if you really want to learn about the transfer learning, I think this notebook is quite complete in a way, especially for the two approaches that I mentioned. So should I go introduce this notebook?
Yeah, sure.
Okay. Yeah. Let's go. I can make it a little bit bigger. Okay. So in this notebook, we have the introduction, talk about why transfer learning, and then why we need the transfer learning and the use case that you can use. Sorry. The first block here is basically to set up everything. When you first open a notebook, you will not have a lot of files. And if you run the notebook, it will automatically download some of the file. So the file that is download is basically the model that I have been trained using the platform itself. For just the example in this case, so I put all the file in Figshare and also the saved of the models that I will use later in the use case later. So it's going to load some file and extract some file. and set up all the environment for you. So if you refresh, you will get the additional files here. So the first section is basically the introduction. The second section of the notebook is basically to introduce the tools for the transfer learning, because I think it could be beneficial for people, because in this notebook, the use case that I will show you is the classification. But transfer learning is not just for the classification or segmentation, but you can use it for any task. So in this section, I basically introduced the tools that is basically you can use for any task. Go through them, each of the tasks. I have the example of the code that you can use the tools for each task. I think I will update it later, but for now, I put, for example, I have the classification and regression. One of the libraries that I recommend using is basically the TIM. You can use it for these tasks. And I have the code that you can load the pre-trained model, and you can use the model directly, or you can fine-tune it. I also put the documentation or the link to the GitHub repo that you can read the documentation if you want to use the library.
Nathan,
Yeah.
there are some comments in the chat that people are having problems with
Oh.
the modules.
Oh, okay. So if you open, can you make sure that it's select the GeoAI?
They said it was using GeoAI kernel, right? Yeah.
Okay. Different use GeoAI kernel.
From TensorFlow.
Okay. Module name TensorFlow. The quick fix for this, you can create the new code block, and then you can just pip install TensorFlow, and then it should run the pip install here. But I thought GeoAI has the TensorFlow. But yeah, maybe I'm wrong. So you can use the pip install and install TensorFlow, and I think it should fix the problem. And basically in Jupyter environment, if you have the error of no module name, usually you can also use exclamation pip install followed by their library. Yeah. But actually in their file that I created is also already included. Okay.
So
Hopefully.
So maybe we can ask Song or Junha, are you still having the issue? Or I was able to run it, and like I guess it had the first one had to finish.
Yeah.
Before that, like
Yeah,
I don't think.
no, I think Jung and I think we have the same issue. This is why I was asking whether the users have different, environments. I think our environment does not preload the TensorFlow, but yeah, I just did the installation waiting.
Okay.
To see
Thank
whether
you.
Thank you. Yeah, so that's something for us to do. Thank you.
Yeah, we will take note, and then we will look into it.
Yeah.
But yeah, but for the Jupyter kernel, I think for the GeoAI on iGuide platform, we have the PyTorch and also TensorFlow included, but maybe it has the conflict with my set up somehow. But thank you for the comments. We will look into that. So, okay, let's go to the tools for the transfer learning. This section, I will not go through it, but I think I added there for the people to, if you have different kind of tasks that you want to actually use the pre-trained model to perform your task, or use the pre-trained model to do the fine-tuning or transfer learning. This section is going to be the place that you can come back and use it as the reference. We have the classification and regression, we have object detection, the NLP, the multitask and rapid prototype, and also the image segmentation. I put the libraries in each of the task, so you can look at how you use those in the iGuide platform. I will just go through it. I will just skip it basically because it's just the example of how you load the model and how you load the pre-trained model and use it. And then I have the summary here for the reference. If you want to use the pre-trained model for any task, I would say you can use the reference here. But the section that I want to start in this notebook is from the transfer learning approaches. Since I use the same image and I already introduced the two approaches that we have in the slide, I will not talk about it too much. We have the feature extraction and the fine-tuning, which we will use in the example. And these are just the example of the code, how you use the pre-trained model as the feature extraction. And basically, you use the ResNet 50. In this example, we use the ResNet 50 as the backbone or the pre-trained model. And we use the segmentation model library to download the pre-trained model. This one is basically you want to do the image segmentation. So I use the segmentation model libraries. It will automatically create a unit model with the encoder, or unit model has two parts, the encoding part and decoding part. In this example, we use the ResNet as the encoding part, and we will use the pre-trained ImageNet weights for the encoding part. And then you can use that as is for the image segmentation. And then for the fine-tuning, is basically the same as you see. We use the base model, but we set the trainable parameter of the layers, the last 20 layers, to true. So we unfreeze some part of the model, and then you can train the model further. So this is how to initialize the model for the fine-tuning. And then the part that I think I want you to look into is basically the use case here. This is the example use case to use the ImageNet pre-trained model to do to fine-tune or to use the transfer learning from the ImageNet model to perform the satellite scene classification. So basically, we start with the UC land use dataset. This is the dataset description. And also, the objective of this section is to perform land use land cover classification and compare between the performance of the train from scratch, the feature extraction, and the fine-tuning approach. And then we will highlight the benefit of the pre-trained model. So first, the start from downloading the preparing dataset. The code here, if you run, it will automatically download the zip file and unzip the file, the dataset into the current folders. But it's already extracted, so you will get the data already. And then this part, we visualize the input data. So the input data is basically the 21 classes, and each classes will have each of the image in the class. For example, the agricultural, you see that is the field, airplane, we have the building, we have dense residential area, forest, freeway. Those are the input data. So, and then for data pre-processing, basically we, when we have the data set, the structure of the folder or the structure of the file in the data set itself might be different. So when we work with the machine learning, it's a good practice to actually create the data loader in order to actually deal with the different kind of the folder structure or something like that. This part is basically the example of how you create the data loader for the model training from the directory. And then if you run that part, it will create the data loader, automatically split the data into the training and the validation using 20% for the validation data and 80% for the training data. The third section of this use case is to create the model using transfer learning. I wouldn't recommend really run this part right now because on the iGuide platform right now, we will train it on the CPU, which will take a while. But I have run it. One thing that I would like you to see in the result is that the first one is for the training from scratch. You will see that the trainable parameter is 29 million parameters that the model has to adjust the weights to the new dataset without the prior knowledge. And everything initialized from the randomization. So it's randomly initialized. So we hope that the model could work with the dataset. So, but also in this example, we train it only for 10 epochs. If you want to actually play with it, you can change the number of epochs here, but it will take a while. As you can see, one epoch takes about 2 to 3 minutes. So yeah, take that, keep that in mind. And then the second case is to use the pre-train on ImageNet and then train only the classifier. So here we load the ResNet 50 as the base model. As you can see, TensorFlow has the pre-trained model that you can just call and use as the ResNet 50, and then you can specify the pre-trained ImageNet weights. And then you do not include the top. Is basically to tell whether you want the classifier or not. In this case, since we are going to train the classifier, we will not use the classifier itself. And then we set all the trainable parameters of the whole base model into the false so that the weights of the ImageNet will not change. And then next, we add these two layers as the classifier for the models. And then we get these new models as the feature models. It specify the input, where is the input and where is the output of the model. And then we compile it, and then we call the fit function to train the model. So the weights that will be adjusted is only for this classifier of the model. And then this one thing that we will see in the model, you will see that the number of the trainable parameter is only 500,000. So the other 23 millions parameters will be frozen, so it will not be adjusted. But you might ask why it takes longer time. It's also because the model, different architecture, the calculation inside the model is also different, even though it might not need to adjust to all of the model, but to pass through the data and also the operation inside the model itself also different than the one that we create from scratch. So it might take a longer time. Also, this model is also, we only train for 10 epochs. And then lastly, the fine-tuning case, the same. We start from initialize the ResNet 50 with the ImageNet, and then we don't include the classifier. Then we only set the last 5 layers for the trainable parameter to true. Other than that, we set it to false. That's why that means we only train the last 5 layers of the ResNet model here. And then the same thing, we add the new classifier to the model, and then we create the whole model here. Then we train the model. This one thing is that, as I mentioned, when you do the fine tuning, we will need to use the smaller learning rates. For the fine tuning or the optimizer, the default learning rate is 0.001. In this case, you see that we don't specify the learning rate. It's basically 0.001. So in this case, we use 0.0001. So it's basically 100 times smaller than their default learning rates. And then we train the model. Since we use smaller learning rates, we train a little bit longer, which is 20 epochs. And then we'll see that the number of parameters also different here. We increase the number of the trainable parameters to 1.5 million parameters. And we train for 20 epochs. What's the setup script does is actually download the saved model and also the history of the training that I have done on the iGuide platform, so that you don't have to actually run it the whole thing. You can stop running all these 3, and then you can just run this part, and you will see the training process, the accuracy and the training accuracy and also the validation accuracy. This plot shows the training process of the 3 training approaches that we did. The blue one is the training from scratch. The green one is the fine tuning, and the yellow one is the feature extraction. So what is shown here? So first, the training from scratch, you see that one thing that we have to see is that at first is interesting that it increased, and also the training and the validation, it follow along really well. But at one point is break apart and is getting bigger and bigger of the difference between the training and the validation. This is the big sign for the overfitting, because at first it worked well between the training and the validation, and then it's just separate. So as you can see, training from scratch has a really, it really depends on how you design the architecture and also how much data, how diverse the data you have. In this case, it might be because the model is too small. It might be because the data set is too small that the model itself overfitting with the training data set and cannot really adapt or works really well with the validation data set. Next is the green one, is the fine-tuning approach. You can see that there are differences between the training and the validation, but the difference is quite constant. The difference is quite constant. So I would say, even though it might have the hint of the overfitting, but it's kind of forgivable in some way, because it can still increase at the same rates as the training process. And you can see that at the end of the 20 epochs that we have, the fine-tuning itself doesn't show strong sign of the overfitting, and also it can adapt to equal or better performance with the training from scratch. So this is the fine-tuning, and the feature extraction, as you can see, it has the lowest performance for the training and also the validation. That is because of the limitation of the adaptation that we set, because the freezing or the ImageNet model doesn't allow any flexibility for the model to adapt to a new task. So only adapting the classifier might not be enough for the data set that we have. So in this case, in conclusion, in this case, I would say the fine-tuning approach might be the best that we should use to do this task. This is the key observation if you want to read more. And then at the end, I also create the visualization of the prediction. You will see that the performance in the visualization here might not be the best, since we only train it for a really short epochs. But you will see that some of the case, the training from scratch might be really well. The feature extraction might not work so well. And some case, the training fine-tuning might be the only case that it actually predict the right one. For this visualization of the prediction result, you can keep rerun it, and you will see different example of the prediction from the validation case. Because we have the trend model here that's saved here, you can rerun it and see different example. And I think at the end is the conclusion, and then the key takeaway. We can go back to the presentation. So next is when to use it, the transfer learning. So if you have limited label data, or you have the idea of how similar between the task that you have and the model that it has. For example, if you have the satellite data set, maybe I would try to use the foundation model from the IBM and NASA to perform the task. Next, if you need to rapidly prototyping the machine learning model, as we shown in the notebook, it will take a really short time and not a huge computational resources to actually see whether the model could perform the task that we want. So it's really helpful to see whether if the model machine learning is even possible to do the task. And also, if you don't have a huge computational resources, you have CPU that you want to train the model on, or if you have a smaller GPU on your desktop setup, you can try to use the transfer learning to actually train the model based on the previous knowledge that the model has. Then, okay.
And there is a question in the chat for training from scratch.
Oh, okay. For training from scratch, do you mean training from random initialized way? Yes. Training from scratch is basically you create a model and then initialize it randomly, and then yeah, that's right. The model learning from no knowledge. Then the feature extraction and fine-tuning are using ImageNet pre-trained weights. Yes. Yes, the model that we use for the fine-tuning and the feature extraction are initialized with the ImageNet pre-trained weights. Yes. That's the correct understanding for those three approaches. And then when not to use the transfer learning, it might not be working for many cases. So if you have a really different data between the pre-trained model and the task that you want, it might not work, but it worth trying, I would say. The availability of the large level data set, if you have a large data set, you might not even need the prior knowledge of the pre-trained model. You can just train it on the label data, and hopefully it perform well with unseen data with the same task. And if you need the high precision, that is also means that you require to have a really large label data set, and you should actually train it from scratch, because that might fit to your needs better. And then if you also have to understand that negative transfer also could happen. Negative transfer mean the data set, the pre-trained model works really well on the task that it has. And then when you transfer it or you use the model for your specific task, it doesn't work at all. Or it works worse than the training from scratch. That is also the risk of the negative transfer. So the key takeaway, when I would say the whole process of thinking of how or when to use transfer learning, first you have to decide whether transfer learning is right for you. You have how big is your data set that you have, how close to the specific task you have with the model that you exist in the pre-trained model. That if the data set, the specific task is too different than the pre-trained, it might not work. That's the first decision that you have to make. The second decision you have to make is to choose the right base model. As I said, there are so many pre-trained model out there. There are many, especially for the model that train on the geospatial data, satellite data, that you can actually use. So choose the right model that you can transfer the knowledge to your task. Then select the appropriate approach, feature extraction or fine-tuning, or other transfer learning approach that could happen, that could be used. But I would say the easiest tool that you can actually use for prototyping or really quickly check whether it would work is the feature extraction and fine-tuning. And then lastly, when you do all those things, you have to also aware of the limitation and the challenge of the transfer learning. For example, you have to also see the overfitting the same as we plot. When you train the model, you have to also look into how the model perform, whether you see the sign of overfitting, or can the model even generalize well to the task that you want. So basically, you have to do the agnostic on the training process that with the approach and base model that you work with. So I think that's all for now. We have like 4 or 5 minutes for the Q&A. If you have any question for the transfer learning, you can speak up.
Yeah, any questions for Nathan on this transfer learning, or maybe even overall on iGuide or anything? We can have informal discussions.
Yeah, I just wanted to ask if the materials for the notebook specifically is available through GitHub, or if it's just through the iGuide, because I was having trouble signing back into iGuide right now.
Yeah, I can send you the GitHub repo, but as I said, the code and also the notebook is actually optimized for the iGuide platform. If you are able to log in, or if you have problem to log in with the iGuide platform, you can also contact me. But in general, the approach and how to use the transfer learning, I can send you the GitHub repo too. Yeah.
Yeah. And I think even the link that is registered on the platform should have the iGuide repo link somewhere. But yeah,
Yeah.
Nathan can do it. Yeah.
Thank you, Albert.
Yeah, thanks.
Can we use our own data in fine-tuning the model? Yes, that's actually because the thing is, I think I might not be clear on the approaches that we use in the use case. In the use case, the ImageNet pre-trained model is actually the large data set of the general image of like cats, dog, table, something like that, like all the general objects. But the data set that we fine-tune it to or transfer the model to is actually the satellite imageries, and it has the class of those scenes. So those are the example of how you could use your own data for the fine-tuning model. In this case, our own data is the satellite scene and also the class of that satellite scene. So if that makes sense. Yeah. Any other questions? Hopefully that answer your question. Yes.
Yes, it does. Thank you.
Thank you so much.
Nathan, maybe you can stop sharing and we can.
Okay, so yeah, thank you so much. If you have any question, you can also contact me, nj7@illinois.edu. Yeah, thank you so much.
Yeah. Yeah, thank you, Nathan. That was great. And yeah, if you have any questions, feel free to reach out to us. And yeah, we'll be here for a few more minutes if you still have questions on this. But also we have weekly VCO schedules, and I'll encourage you to join whenever possible.
Great job. Thanks, Nathan. Since there were issues experienced by some of the participants, I was wondering whether in this VCU and in the future ones, it might be a good idea to share how to report the issues.
Okay, yeah.
Beyond using chat and just telling us directly.
Thank you.
Yeah. So that's a good thing. So we have help at i-guide.io, i-guide.io, and you can definitely send us tickets there, and we'll be able to get back to you if you have any problems. And also there is a help button on the top of the iGuide platform page, which could be used. But Chavan, that's a nice point. We can emphasize that even at the beginning, the future.
Thank you.
Thank you, everyone. Anything else before we wrap up today's meeting? Thank you all.
Thank
see
you
you
so
next week.
much. Bye-bye.
Bye.
Thanks. Take care.